Okay, cool. Thanks, Char. Yeah, so today I'm going to be talking about two papers. The first is from this Fox 2023 paper, Fox 2023 with a variety of people. And the second is just with my student Will at Brown. So I work on graph algorithms, and this is a talk about graph algorithms. And I don't know what like normal people dream about at night, but when I'm like cozily tucked away in my bed, I have these like very pleasant dreams to myself about how it would be like so great if every graph were a tree. So what do I mean by that? Well, my running example today of a problem is going to be the Steiner tree problem. So as a reminder, in this problem, we're given a graph. Edges have non-negative weights, and we're also given a subset of terminals, which is a subset of the vertices. So an instance like something like this, where in blue, I have this terminal set of vertices, and a feasible output in Steiner tree is just a subset of the edges, so a subgraph, which connects all the terminals, where my goal is to minimize the total weight of the edges that I choose. So for instance, this set in blue is a feasible solution. This set in blue is another feasible solution. This is another feasible solution. And now my goal is just to like minimize the total weight I use among the edges that I choose while guaranteeing that all of the, in this case, blue nodes are connected. Okay. So part of the reason people have studied this problem so much is because it's like a nice way of modeling network broadcasts. So if you imagine that sort of like sending a message over one edge costs me something, and one of these nodes has a message for all the other nodes, then finding a good Steiner tree solution is a way of figuring out how to broadcast that message to all the other nodes while minimizing the total cost of the broadcast. So I have a bunch of these. These are questions for the audience. So far I haven't said anything about trees, but of course this is called Steiner tree. I mean, can somebody maybe tell me why this problem is called Steiner tree? Not just, I don't know, Steiner subgraph or something like that. Hopefully not a trick question. Yeah, exactly. The optimal solution cannot contain a cycle, assuming non-negative edge weights. So you might as well assume that you're just trying to optimize over trees which connect the terminals. Okay. Here's another question for the audience. Does anybody see what the optimal solution is here? Say, assuming that each edge has weight 1. Yeah, it's like not clear. I mean, like I don't see the optimal solution either. And you can be forgiven for not immediately seeing the optimal solution because this is in fact one of Karp's original 21 NP complete problems. So it's like a non-trivial computational problem to try to solve. Now here's like a different problem, super fun problem that I just made up. I'll call this Steiner tree on a tree. The setup here is exactly the same as before, except my input graph is actually just a tree. Okay, so here's my input graph. I'd like to connect the blue nodes. And now if somebody like walked up to you on the street and they're like, hey, what's the optimal solution? Assuming non-negative edge weights for this instance, I mean, like, what would you say? It's actually a question for the audience. Yeah, I mean, just take like the minimal subgraph of my solution that connects all these blue nodes. There's sort of like one obvious optimal solution. Okay, any other edge is like unnecessary and will just hurt the quality of your solution. Okay, so in this way, we're allowed to assume that our input graph is a tree. We like totally trivialize our problem from a computational perspective. Okay, so my fun new problem here is definitely not one of Karp's original 21 incomplete problems. And in fact, it's like trivially incomplete. Okay, so of course, like every graph is not a tree. And in general, we want to solve problems on an arbitrary graph. So like what use is this observation that we can like trivialize our problems if the input graph is a tree? Well, it's like a simple observation, but it allows us to instantiate what I'll call the tree embedding framework. Namely, imagine that we start with some arbitrary problem, say Steiner tree, or a problem on an arbitrary graph, say Steiner tree. Then what we can do is we can like take our arbitrary graph, we can hopefully approximate it well with the tree. Then we can just like use the fact that this tends to trivialize our problems to solve our problem on the tree, things like solving Steiner tree on a tree rather than an arbitrary graph. And then hopefully we can like project our solution back to the original graph and up with a solution for the actual problem that we're trying to solve. And maybe if this approximation is good, like this tree is a good approximation for the original graph, we will expect to not lose too much in the quality of the solution that we end up with. Okay, so this is like a framework which has been used with great success for many different kinds of problems. So it's been used for like clustering, dynamic algorithms, online algorithms, network design, routing algorithms, distance oracles, solving STD linear systems, and recent breakthroughs in almost linear time algorithms for web. And this is all to say that like people care about approximating arbitrary graphs with trees, and it's been enormously successful in graph algorithms. So, of course, if like this is your framework, you might naturally ask like, well, what do you actually mean by like, approximate the input graph with a tree? And there are like two things that we have to be careful about here. So the first is like, what kind of tree are we talking about? In particular, I'm going to distinguish today between non-spanning tree embeddings and spanning tree embeddings, where a non-spanning tree embedding is constructed in the following way. Like you imagine you start with your input graph, you just forget about the edges in the original graph, and then you allow yourself to construct a tree that uses any edges that you want. So like some of these edges, say this one, are edges in my tree that are not edges in the original graph. Okay, so such a non-spanning tree embedding is sort of like nice because it becomes easier to figure out how to approximate your graph by the non-spanning tree, because basically you have more flexibility, right? You can use edges that were not in your original graph. But then it becomes harder to figure out how you're supposed to project this back to a solution on your original graph, because like, well, maybe your solution chooses this edge, say in like Steiner tree, but this is not actually an edge in the original graph. So it may not be entirely obvious like what edge you should buy in the original graph, if this is the kind of tree embedding that you're using. On the other hand, and what I'll be talking about mostly today are spanning tree embeddings, where the way you construct this is you like, throw away edges in your graph so that a tree remains. And in particular, the tree that you use to approximate your original graph is a subgraph of the original graph. Okay? Okay, so now the second question is like, what do I mean when I say approximate the input graph, an arbitrary graph? Like there are many senses in which you could hope for a tree that approximates the original graph. So you can imagine approximating cuts or flows. For the purposes of today's talk, and I should say actually, yeah, so it becomes harder to construct these things if you restrict yourself to using edges in the original graph, but it becomes easier to understand how to project it back into the original graph, because now an edge in the tree corresponds to an edge in the original graph. So if you choose this edge in your tree solution, probably you should choose this edge in the original graph. Okay. And a lot of the applications that I gave require that your tree embeddings are spanning trees. Okay, so what's the sense of approximate? Well, for the purposes of today's talk, I'm basically going to be talking about approximating distances. So over here, you have some metric, which is the shortest path metric, where the distance between two nodes is the minimum weight of the path that connects them. Over here, you similarly have some shortest path metric. And what I'd like is that if you think about any two nodes, that their distances according to these two metrics are approximately the same. So picture is like, you think about two nodes over here, the same two nodes over in your tree, and the weight of the minimum weight path connecting over here should be approximately equal to the weight of the minimum weight path connecting over here. Okay. All right. So basically, summarizing, what I'm going to be interested in today is understanding this tree embedding step, and in particular, understanding how to approximate graph distances with spanning distances. All right. So at this point in the talk, you should like ask yourself a question, which is like, should we dream? And more specifically, like, should we dream of approximating graph distances with spanning tree distances? And if you thought about this for, I don't know, like more than 5 minutes, you very quickly realize that things look pretty bad for this goal. Namely, imagine I give you just like a cycle where every edge is weight 1. And now I'd like to approximate distances in the cycle with a spanning tree cycle. So of course, any such spanning tree is just going to like leave some edge out without loss of generality in that one. But now, of course, if you like look at the two vertices that were on either side of this edge, in the original graph, their distance was just 1 because there was like an edge connecting them with weight 1. But over here, now they have to like traverse the entire cycle to connect to one another. Okay, so things look pretty bad. And like maybe you have to multiply up the distances over here by a factor of n, where n is the number of vertices in the graph, in order to get those distances to be anywhere near these distances. And, it's like a linear approximation factor that doesn't look so great. So the answer is no, but now you might hope like maybe we can like mostly approximately preserve distances or something like that. Like maybe if we relax our goal more, we can hope to achieve something non-trivial. And this is sort of the right intuition. So basically, people have come up with all sorts of ways of basically fighting it against this cycle counterexample. So if you accept distribution over spanning trees rather than a single spanning tree, and you only care about preserving distances in expectation, then all of a sudden you can get sort of polylogarithmic guarantees. These are called probabilistic tree embeddings. If you only care about preserving distances for most pairs, you can also achieve non-trivial guarantees. These are called Ramsey embeddings. If you want to give like a collection of trees, where for any two nodes, there's some tree in that collection that preserves distance as well, you can hope for non-trivial guarantees. They're called tree covers. And lastly, if you care about rooted subsets in a sense that I'll clarify in a little bit, you can also achieve non-trivial guarantees, and these are called universal Steiner trees. All this is to say that like there are many ways of taking this impossibility result of the cycle and slightly tweaking the goal of what we're hoping for, namely the sense in which we want to preserve distances with spanning trees in ways that are still algorithmically useful, but like allow you to obtain non-trivial guarantees. There's like many others. Okay. Any questions about that? This is all just sort of like context and vibes at this point. I should say like this talk is going to be a lot of like definitions and vibes, and all the proofs are at the end. So we may not get too many proofs, but I'm hoping that like the perspective and the vibes are going to be used. Okay. I'm sorry to make you follow me. So the focus of today's talk is going to be on these like universal Steiner trees. And in particular, I'm going to start by telling you all about what universal Steiner trees are and some of the results we were able to obtain for them. Then I want to give you all this like different perspective on universal Steiner trees that's all about sort of like vertex hierarchies. Then I want to take a step back and apply this perspective to just like tree embeddings in general and tell you about some of the results we were able to get there. And then, I mean, like hopefully if I have time, we'll do some proof sketches, some like cute animations in here. So I hope we'll get to them. All right, so what are universal Steiner trees? So informally, a universal Steiner tree is just like a single spanning tree that is a good approximation for all instances of Steiner tree on your input graph. Okay, so more formally, row approximate universal Steiner tree for a graph G and root R is just like a spanning tree of the original graph. So you're like throwing away edges, but you just have a tree, such that if you look at the cost of the optimal solution in your tree that connects any subset S, that cost should be at most rho times larger than the optimal solution for connecting that subset S in the original graph. Okay, so the picture over here is like you're looking at this single fixed subset of the vertices. There's some cost in the original graph over here, and then there's some cost in the spanning tree over here, and this cost should not be that much larger than that cost. Okay, and in particular, this cost can only be larger than that cost. Why? Yeah.
Because we have less edges.
Yeah, we have like fewer edges, so there's like fewer things that we can put into our solution. Okay.
So are you assuming that the weights are always
The weights are going to be unchanged. Yeah, and in fact, that's sort of like without loss of generality. Like it never kind of helps you to modify the weights over here. Okay, so there's like one thing that I haven't actually said anything about, which is there's this like weird root business floating around. In particular, I'm assuming that there's some root R such that the subsets that I consider connecting always contain this root R. So this is sort of like one terminal here R that I'm going to assume is always in the terminal set of the instances of Steiner tree that I'm trying to approximate with my spanning tree. Okay, it's like looks a little bit funny. Of course, like Steiner tree does not have this requirement of there being like some root that's always in it or something. It's just about a subset of terminals. So we'll get to that in a second. I guess just to sort of like close the loop on what this has to do with distances. I mean, I claim that if rho is 1, then in some sense this is just a strengthening of a shortest path tree, which is to say it's a subgraph of the original graph that preserves all distances to R. Why is that? What's that?
That's one instance.
Yeah, that's like one instance of Steiner tree, right? Like if your terminal set is 2 vertices, or yeah, if it's 2 vertices, the optimal solution for Steiner tree is always just the shortest path connecting them. Okay, so for rho equals 1, this is just a shortest path tree. So you can sort of think of this as like an approximate shortest path tree that's supposed to work for subsets of vertices instead of just pairs of vertices, where one of those pairs is always the root. Okay, everyone good with what a shortest path tree is? Okay, so here's my next question about this, which is like, why do I need this root assumption? In particular, I claim that if I want to achieve sublinear approximation guarantees, it better be the case that I can assume that there's some root, which is always in the instance of Steiner tree that I want to solve. In particular, if I modify my definition to look like this, then there's no hope for row sublinear in n, where again n is the number of vertices in my graph. It's a cycle, exactly, right? So yeah, why do we even need this root assumption? Well, it's really, the way that universal Steiner trees are trying to get around this cycle counterexample, right? So if you think about, like, suppose that was your definition for universal Steiner tree, and now you're supposed to come up with a good universal Steiner tree for the cycle. Of course, I could come along and be like, okay, well, like, give me a good Steiner tree connecting this pair. The optimal solution in the original graph is the shortest path, which is just this one end. But the optimal solution in your claimed universal Steiner tree has to go all the way around. So now rho is going to have to be at least omega n. Like, you've blown up the cost of your universal Steiner tree by a factor of essentially n. On the other hand, if I can assume that there's some root, which is always in my terminal set, and I leave out, in order to construct my universal Steiner tree, the edge on the opposite side of the root in my cycle, like, sure, you can come along and be like, okay, connect this pair of vertices that are on either side of this edge. But now, like, over in the original graph, you're also forced to connect the root, and you have to pay something like n/2 over here. And over here, you still have to pay like n. So now there's hope for rho being a factor of 2 or something like that. Okay, so the root assumption is really how we're like dealing with the cycle. Good. All right. So part of the reason that people originally studied universal Steiner trees is like they proposed it as a better way of modeling broadcasts, right? Like, if you imagine that you're given like a fixed network and you're trying to like broadcast in this network, like, probably you don't want to be resolving a new instance of Steiner tree over and over again if that's very computationally expensive. Now what you can do is you can like sparsify your graph down to just a universal Steiner tree, and now as sort of like terminal sets show up, it's sort of trivial computationally to figure out how to connect them according to your universal Steiner tree. So it's supposed to be like the better model of, in particular, repeated broadcasts in a network. Okay. This is just sort of like why people originally pitched these objects. So let me tell you all a little bit about what's known about this and what we showed. So there's this paper from Stock from about 20 years ago that showed that there are some graphs where you better pay at least a log n factor in the quality of your universal Steiner tree. Okay, so here's like our lower bound. We're going to pay at least log n. There's a Fox paper from about 10 years later, which showed that you can achieve universal Steiner trees with this very funny approximation guarantee, 2 to the O of square root log n. So I sometimes have heard people refer to these as Mary Poppins bounds because they're super polylogarithmic sublinear, which I guess sounds like the Mary Poppins phrase. Not a lot of Mary Poppins fans in the audience today. So basically, this is larger than any fixed polylogarithm in n, but it's asymptotically like little o of n, or in fact, any polynomial in n. So it lies somewhere between, you should think, like polylog n and n. So it's like non-trivial. It's not n, which would be easy to get, but it's much worse than the kind of like lower bound we have, which is polylog. Okay. So I've drawn these in like large font pretty close to one another, but for the purposes of approximation algorithms, you should think of this as being like very far from that. Oh, good. Yeah, PTC. Yeah, I'm going to write that in a few places. Polytime computable. I mean, you would sort of get like polytime algorithms out of all these results, obviously by construction. So I'm not going to be talking so much about the algorithm to construct these things. So it'd be like a little footnote as PTC. Yeah, thank you. Okay, any other questions? Okay, but like, not exactly, but basically this is exponentially larger than that. Right? Like n would be exponentially larger than that. This is almost n. Okay, so the technical term here is there was like a big gap. And what did we show? Well, we showed that actually you can achieve like polylogarithmic-quality universal symmetries. Okay, so in some sense we just like shrunk this gap down. So what polylogarithm like log to the 7th? Okay. Interesting thing is not necessarily like the specific polylog here, but just the fact that the right answer is not this like Mary Poppins type out. Good. Right. So I should say that there's also been like a lot of work on universal Steiner trees for various like special restricted graphs, like planar graphs or bounded doubling dimension graphs, whatever those are. It's not so important for today's talk, but this is all to say that just like people have been thinking about these objects across like many papers. But for the focus of today's talk will really just be about the fact that there used to be this like super polylogarithmic upper bound, and now we have a polylogarithmic upper bound. Yeah.
That was if you look at the expectation, so the qualifier is On the distribution of trees such that for every pair, for every subset, the expected cost is not still log n, or
Yeah, so then you can just take like a regular probabilistic tree embedding and you can get a log bound to these.
and the type, the low bounds to work.
So if you have no prior knowledge about like the terminals that show up, then yes. There's this nice other question which is related to this thing called a priori TSP, where like maybe if I have a distribution over the vertices that I care about, and I'm also taking expectation over that randomness, then as far as we know, you could get constants. But if it's a worst case over all terminal subsets, then log n is tight.
The distribution, you assume some structure, otherwise we must not say here.
Yeah. Like it's like independent arrivals of That's like a little pet problem of mine that I'm gonna need to give to somebody to solve. Trying to get a constant for that version. Okay, so this is the status of the universal Steiner tree. So now we've gotten through our first point. Now I want to like take a step back and tell you all a little bit about how prior results for universal Steiner trees and how our result were. So I'll tell you about what I'm calling the hierarchy for universal Steiner trees. So again, our object of desire is the universal Steiner tree. So what we'd like to do is we'd like to start with an arbitrary graph and then like sparsify it down to just a single spanning tree. And in particular, this prior work gave a 2 to the root log n quality universal Steiner tree. We gave a polylogarithmic-quality universal Steiner tree. And the way that we gave these things is we didn't just sort of like in one shot go from the graph to the tree, but rather we went through this sort of like intermediate step of some kind of vertex hierarchy. In particular, both prior work and our work take our arbitrary graph, construct some kind of hierarchy on the vertices, and show that like if you can come up with a hierarchy of some quality, say Q, then you can come up with universal Steiner trees of basically the same quality, some like small polylogarithmic loss. Okay, and so basically the way that this prior work and our own work works then is that like the prior work showed that you can get quality of these hierarchies from 2 to the root log n, and we showed that you can improve that quality to polylogarithmic. Okay, so ultimately all the gains in our result are just going to come from improving the quality of these hierarchies. Okay, so now I want to tell you all like what these hierarchies actually are, because I think they're kind of interesting in their own right. So in order to tell you what this hierarchy is, I need to tell you what like each level of the hierarchy is. So this is going to be a hierarchy of things called sparse partitions. A single sparse partition is just going to be a vertex partition where balls intersect few parts. The rough picture here is that you have all of your vertices, you like partition it up into a set. This is supposed to be your sparse partition. Now, if you look at like any ball in the graph of like nearby nodes, then that ball should not intersect too many parts. Okay, so like this ball intersects maybe like 3 parts. Okay, that's like the informal perspective. To give you all the formal perspective, I can just a little bit more vocabulary. So the strong diameter of a subset of vertices is just the maximum distance between 2 vertices, where I only allow myself to use edges inside of that part. So the strong diameter of this set is just the maximum distance between 2 vertices if I throw away every edge not in this set, and then I ask myself like, what's the distance between vertices in this so-called induced graph? Okay, so this would have like this set has diameter 1, 2, 3, 4, assuming unit weight edges. Okay, then the strong diameter of a vertex partition. So now I have maybe like many parts is just the maximum strong diameter of any one of these parts. Okay, yeah.
Why do you call it strong diameter?
Yeah, so people differentiate between this and weak diameter, where the weak diameter of a subset of vertices is the maximum distance between any 2 vertices in that set, assuming you're allowed to use edges both inside and outside of that set. So here, okay, this is not a great example. Let's find one that's interesting. Yeah, I'm not sure I have a good part with a strong and weak diameter are very different.
Like you might be able to like jump outside.
Yeah, exactly. Yeah, the question is whether or not you can jump outside and use this path.
Like the wheel with the vertex in the center.
Yeah, exactly. Yeah. So if you had like a wheel with the vertex in the center connected via spokes to all the other things, and you're thinking about the diameter of just the outside cycle, then it has like strong diameter like kind of over 2 or something, but it's weak diameter like 2 because you can jump to the middle. Yeah. Hopefully my hands were clear. Okay. So this is the diameter of a partition. And now I can formally tell you all what a sparse partition is. So a vertex partition of diameter delta is said to be alpha tau sparse. So there are 2 parameters really that go into this. If you look at any relevant ball, what is a relevant ball? it's a ball centered at a vertex V whose diameter is basically the diameter of the partition divided by alpha, where you should think of alpha as being larger than 1. So you're sort of looking at balls that are the diameter of your partition shrunken down. And this ball should intersect at most tau parts. Okay, so the picture over here is like this partition is sparse. If, well, first of all, it has Mohs strong diameter. So the distance between any two vertices within one part is small. And furthermore, if you think about the entire graph, and you think about any vertex, then if you draw a ball whose radius is basically the diameter of these parts, but shrunken down by this alpha factor, that ball should not intersect too many parts, namely at most tau, or in this case, 3. Okay, so shrunken down balls intersect small number of parts, where like the size of these balls is dictated by the diameter of the partition. So, question for the audience, they claim that if you give me any delta, and my graph is just a path, then for any diameter delta, I can come up with a partition that is alpha tau sparse for alpha and tau some small constants. So here's my path. So anyone want to tell me how to come up with a sparse partition with diameter delta? And it's probably the first thing you think to do.
So cut it every double step.
Yeah, just cut it like every double steps. And here, imagine double those like 2. And now, if you look at any ball of radius, say delta over 2, this is a ball of radius delta over 2 centered at this vertex, it can intersect at most 2 of these parts, no matter which sort of like where you center this ball. Okay? This is like a common theme in graph decomp systems like this. For the path, it's very easy to come up with a construction that achieves constant parameters. Then when you move to arbitrary graphs, you pick up a log n. So we know how to achieve parameters alpha and tau of log n. So if you shrink your balls down by log n, then they intersect at most log n things. This is actually kind of like a reanalysis of this nice result from parallel algorithms, MPX, if you know what that is. And it's tight in the sense that log is necessary. If, in particular, if you want to achieve O of log n alpha, you need omega of log n and tau, vice versa. But you should just think of like log n is like the right answer for both parameters and general graphs. That's what I want you to remember. Okay. Any questions? So this is like one level of our hierarchy. And then the entire hierarchy is going to give us universal Steiner trees. Yeah.
So you want like constant alpha or constant tau, you gotta go and compare the other one?
Yes. Any other questions? Yeah. Okay. So what is the hierarchy of these things? Well, as far as hierarchy of these things is just like a series of coarsened sparse partitions. So the bottom level is going to be like a very low diameter sparse partition. One level up will sort of be like a coarsening of that. So you're like grouping together the clusters. One level up again will like group together some of these clusters until you get your final level, which groups everything together in just like one cluster part of your partition. Okay, so more formally, I'll be talking about hierarchies, but I really mean like hierarchy of vertices. So a vertex hierarchy is just a series of partitions where the bottom partition is the singleton partition, think like this blue one. So it just puts everybody in their own part. The top partition is the trivial partition, which puts everything in one part, think like purple partition here. And each of these partitions coarsens the previous one in the sense that it's formed by the disjoint union of parts from one level down. So like this red set is the union of this B set, this one, that one. Okay. Hopefully I don't need to write like more technical ways of describing like maybe the coarsening. Now I'll say that the hierarchy is alpha tau sparse if each of the levels of it is alpha tau sparse. Okay. So at this point you should be like, like, these hierarchies actually seem like pretty easy to come up with alpha and tau of 1. In particular, I claim it's trivial to get an alpha equals tau equals 1 sparse hierarchy so far. Can somebody tell me why? Yeah, very good. Excellent. Yeah, so right, like I could just have 2 levels like this, and now the diameter of this bottom one is 0, so the relevant shrunken down balls are also diameter 0, which is to say that any relevant ball will only intersect one part. At the top level of this hierarchy, okay, like the diameter of this thing is like the diameter of the entire graph, but there's only one part for things to intersect. So draw whatever ball you want, it's only going to intersect one part. Okay, so far it's like trivial to get like good sparsity hierarchies, and we want some knob we can turn to basically prevent you from doing this. And that knob is what I'll call gamma growing. So we'll say that the hierarchy is gamma growing if each level of the hierarchy has diameter at most gamma to the I. And in particular, if you think of gamma as like, say, a constant or something like that, it prevents you from making the first level of your hierarchy have diameter 0, and the last level have diameter something huge, the diameter of the graph. Like the second level, when you go one level up, is only allowed to have diameter at most like gamma squared. Okay, so if gamma is small, then you can't just do this big jump from trivial partition to trivial partition. Okay, and you should think of like smaller gamma as like harder to achieve and more interesting as far as the hierarchy is concerned.
Oh, I tend to they're equal to a lot of trivial division and then manually allowed.
Yeah, I mean, okay, you should think of, I'm gonna say at most, you should think of the diameter as being basically exactly equal to gamma to the I. That's just
gamma to the ML1 and gamma to the I.
what's yeah. I mean, I'm gonna say gamma growing, but yeah, just imagine that the diameter of the ith level is actually just, let's say, I mean, even for simplicity, exactly gamma to the I. Good question. Okay. So I said that these hierarchies have something to do with universal Steiner trees. So formally, here's what was shown in this earlier Fox paper. It was shown that if you give me alpha, tau, sparse, gamma growing hierarchies, as long as gamma is at least like log squared n, then you can in polynomial time compute a good universal Steiner tree whose parameters are basically some smushed together polynomial in all of these parameters. So it's like alpha squared times tau squared times gamma times log n. Okay. So all this is to say that if you come up with good hierarchies, you can come up with good universal Steiner trees, where the carryover in parameters just picks up basically a log n, and like a polynomial in the quality of the parameters. Okay, so then what did this previous paper do? Well, they showed that every graph has a gamma growing alpha tau sparse hierarchy whose parameters are this Mary Poppins bound, 2 to the O of square root log n. Okay, so you just take the quality of hierarchies here, you plug them in for the parameters up top, and you get your universal Steiner trees of quality, essentially 2 to the O of square root log n. Is that clear? So get Mary Poppins bound here results in Mary Poppins bounds there. Okay, so what did we do? Well, we just kind of like improved the quality of these hierarchies from Mary Poppins type bounds to logarithmic bounds. So we showed that you can get alpha equals tau equals O of log n with gamma of log squared n. And remember that for even just a single level of these sparse partitions, alpha equals tau equals log n is tight. So this is basically like an optimal version of these hierarchies up to this log squared factor of gamma. Like the values of alpha and tau here are optimal. Good. All right. So this is like the hierarchy perspective on universal Steiner trees, right? Like if we want to get good universal Steiner trees, in some sense, it suffices to just construct a particular kind of vertex hierarchy of good quality. I'm not going to tell you all too much about how we do this, but maybe I'm going to be talking about sort of like why we do this in the next part of this. All right, so this is the hierarchy perspective on USTs. And now I want to turn to talking about tree embeddings more generally. So yeah, actually, how long do I have? Is it an hour from when I started? Yeah, this would be 25 more minutes. Okay. So let me tell you a little bit about a little journey I've been on this hierarchy perspective on tree embeddings. So, this is the picture I just drew for you all of these like universal Steiner trees, right? You get these hierarchies and then you get the universal Steiner trees. But of course, at the beginning of this talk, I told you about how there are all these different senses of tree embeddings, right? There's lots of many different ways, all trying to do battle with a cycle example, in which we can like try to approximate graph distances by an arbitrary graph with spanning tree. Okay, or maybe a distribution over spanning trees or like a collection of spanning trees in the case of two. And so, you might ask, like, we know how to get universal Steiner trees by taking this intermediate step through hierarchies, these like sparse partition hierarchies. What about these other things? Like, how do we normally construct those? And at least in explicit terms, the way that we construct all these different senses of tree embeddings is not through hierarchies, and they could do something. We know good constructions of these things, but none of them, in explicit terms at least, like go through a step, like trying to first construct a hierarchy and then turn that hierarchy into a tree embedding. Okay, and some of these constructions are actually like extremely complicated. So, for instance, the construction of Ramsey tree embeddings is like no shade to the authors, but like it's a grind. It's like not fun to try to understand. Okay, and the question that I became interested in is basically like, is there some sort of like nicer picture here where we can understand each of these tree embeddings as similarly to universal Steiner trees, instantiating some hierarchy. Like it's really just like a good representation of some kind of hierarchy in the original path. So in order to tell you all a little bit more precisely about what I mean, I need to introduce this sort of like embedding perspective on hierarchies. Okay. In particular, I'm going to tell you all about like what it might mean for you to take a hierarchy and to embed just an arbitrary hierarchy into a tree. And if you want to talk about embedding an arbitrary hierarchy into a tree, and in particular the distances of an arbitrary hierarchy into a tree, I have to tell you all what the distances in an arbitrary hierarchy are. Okay. So, just a little bit of notation. I'm going to let I and B just be the smallest I, like the smallest level of the hierarchy, such that U and V are in the same part of the ith level of your hierarchy. Okay. And then, assuming this is like a gamma growing hierarchy, I'll let the hierarchy distance between vertices U and V just be gamma to the IUV. So the way that I'm measuring distance between two vertices, according to my hierarchy, is I take those two vertices, I look at the first level of this hierarchy that has the part that contains both of them. So in that case, it would be the green level here. And then I ask myself, essentially, like, what is the diameter of that level of the hierarchy? Okay. And the diameter of that level of the hierarchy will tell me the distance between these two vertices according to the hierarchy. So a cute little exercise, you can convince yourself this is a metric. Okay. So this is like a sense in which you can think of a hierarchy of vertices as inducing distances. Okay. What does this have to do with tree embeddings? Well, I'll say that subtree, subgraph, my original graph, BT, is a gamma distortion embedding of the hierarchy. If basically you preserve all distances, lambda distortion embedding, if basically you preserve all distances up to this multiplicative lambda. So in particular, the distances between any two vertices U and V should only, in the tree, be at most lambda times their original distances, and should only be larger than their original distances. So the picture here is like you have two vertices that you're interested in. Here they are in the hierarchy, here they are in the tree. And what you want is if you measure their distances according to the hierarchy, that should be essentially the same as their distances according to the tree up to this lambda fab. Okay. This is the sense in which we can hope for a tree that approximates the distances of the hierarchy. Is that clear? This is actually a very important definition. Let me hang on this for a second. Yeah, somebody asked me a question. Yeah.
Does this tree have to be a spider tree or something?
Yeah, so more on that later. By default, let's say yes, but I'll talk about that in a little bit. Good question. Okay, so far I've just like pulled out of a hat some sense of the distances of a hierarchy and told you all like, well, you could hope for a tree that preserves those distances. What does this have to do with universal Steiner trees and tree embeddings and all of that? Well, you can interpret this previous result and says that if you give me a sparse gamma growing hierarchy, then I can give you back a universal Steiner tree is really just like an embedding result. I mean, this is very much not the language of this original paper, but if you stare at it long enough, what you'll realize is that this theorem is really composed of two parts. It's composed of one thing that says tree embedding of a sparse partition hierarchy is sufficient for a universal Steiner tree, and a second part that says tree embeddings of sparse partition hierarchies exist. Okay, you put these two things together, and you'll find that you can go from a hierarchy to a universal Steiner tree, in particular a sparse hierarchy to a universal Steiner tree. Okay, so a little bit more precisely, this first point says that if you give me any lambda distortion embedding of a gamma growing alpha tau sparse hierarchy, so this is just like one of these sparse partition hierarchies, if you embed that into a tree, that tree will always be a good universal Steiner tree, where the loss in the quality, the universal Steiner tree, is just like all the parameters smushed together with like an extra log. Okay, so this is just, again, to say a tree embedding of the hierarchy, these sparse partition hierarchies, is sufficient to come up with a universal Steiner tree. Second point here says, well, we can actually come up with tree embeddings of the hierarchy. So if you give me any gamma growing alpha tau sparse hierarchy, it always has a lambda distortion embedding into like a tree. As long as gamma is at least log squared n, and the quality of this embedding, like the lambda factor here, will be alpha times tau. So you'll notice that if you take this parameterization for lambda, alpha times tau, and you plug it in there, you get back alpha squared times tau squared times gamma times log n, which is exactly the quality of the universal Steiner trees we get, okay? So this is all to say that really the way you should think about how we go from hierarchies to universal Steiner trees is we show it's possible to embed the distances of sparse hierarchies into spanning trees. And that's like enough kind of a universal Steiner tree. Let me pause for a second. There's a lot of like with tech on this slide and parameters flying around. But hopefully the 1 and 2 make the deal clear. Any questions? Maybe I'll just reiterate. So the point here is that what this result is saying is if you have a sparse partition hierarchy and you embed those distances into a tree, that tree will be a universal Steiner tree. Okay. But now jumping back to all of our different kinds of tree embeddings, we can like ask whether or not this applies for these other tree embeddings. In particular, this result said that a tree embedding of sparse partition hierarchies is sufficient to come up with a universal Steiner tree. So now we can like try to backwards engineer what kind of hierarchies we might need for these other notions of tree embeddings. We can say, well, what kind of hierarchy would be sufficient for tree covers if we were to embed its distances? What kind of hierarchy would be sufficient for random embedding? What kind of hierarchy would be sufficient for probabilistic tree embeddings? And what you find is that like actually there's already well-studied versions of vertex hierarchies that you can think of sort of like sparse partition hierarchies, but with different kinds of guarantees, such that if you could take any one of these sensitive hierarchy and embed those distances into a tree, then you'd end up with these kinds of tree embeddings that you want. And what's so nice about this is actually like coming up with these hierarchies is much simpler than coming up with the tree embeddings themselves directly. Like if you want to construct a hierarchy of LDPs, low diameter decompositions, it's very easy to do that in a way that's much easier than trying to like go straight for probabilistic tree embeddings, which are spanning trees. The downside of this, though, is like, we know that if you could embed, say, this hierarchy into a tree, then you would end up with a good, say, probabilistic tree embed. But we don't know that tree embeddings of these other sensitive hierarchy exist. Like this previous embedding really used the fact that this was a sparse partition hierarchy to come up with an embedding into a tree to get a universal Steiner tree. Okay, so we don't know how to go from these hierarchies to these notions of tree embedding. Okay, we know that if you could embed each of these into a tree, each of these sensitive hierarchy into a tree, then you would come up with the kind of embedding that you want. Okay, so at this point you could say like, well, that's all fine, Ellis. Like what I'm going to do is I'm just going to redo what we did for universal Steiner trees, but for all of these different kinds of hierarchies. In particular, you could go to this, say, neighborhood cover hierarchy and say like, well, if I can use the properties of neighborhood covers to argue that neighborhood cover hierarchies can always be embedded into trees, then I'll have, in this case, the tree covers that I want. Okay, and you can do the same thing here and the same thing there. And you can do this, but like, it might be here for a while. Like, there's lots of different sets of tree embeddings. You'd have to come up with a different embedding for each of these hierarchies into trees. So you'd have this like, little bespoke series of theorems, one which works for each one of these. And the kind of provocative, I think, question that we asked is like, well, what if we can just embed any hierarchy into a spanning tree? Okay, so rather than trying sort of like go to each one of these sensitive hierarchy, use its properties, things like these sparse partition hierarchies, what if I can just show that the distances induced by any hierarchy can always be well represented with a spanning tree? This would be great because then we wouldn't have to try to like recreate the step for universal Steiner trees for every other sense of tree embedding that we might be interested in. Okay, now coming back to your question, I claim that if I do not want a spanning tree, it's trivial to get constant distortion. It's somewhat trivial to get constant distortion. So I give you any hierarchy, and I'm like, now I want you to represent the distances in this hierarchy with a tree, but you can like make up edges and assign them whatever way you want. Maybe imagine I can also add vertices if I want. I claim that I can come up with a good embedding of the hierarchy distances into a tree. And there's kind of only like one natural thing that makes sense here. Maybe I'll let somebody suggest it.
For every class, every.
Yes, very good. Right? So like what I'm going to do is I'm just going to kind of like obey the structure of the hierarchy, which is to say that, okay, this bottom of the hierarchy is boring. Like each of these parts, clusters, consists of just a single vertex. Go to the green level and just like connect up all these things in like a star-like fashion. right? So for each cluster, just connect them as a star, connect them as a star, connect them as a star, 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 star. Okay. Then let me just take each of these stars, and for the red level, I'll connect each of the green centers of my star to the star. Over here, green centers of my star as a star. For the purple level, I'll connect the red centers. Okay. Now, what weights do I use? Well, basically just set the green edges to have weight gamma, the red edges to have weight gamma squared, the purple edges to have weight gamma to the third, and so on. Okay. Now, what you'll find is that, like, if you're trying to measure the distance between, say, these two vertices, in the hierarchy, their distance is like gamma, and in this tree, their distance is like, well, 2 gamma. They have to go through here. Ditto for any other two vertices. Okay. So it's like trivial to put very good embeddings into trees if you don't require that they be spanning trees of the original graph. Okay, so this should make us hopeful. On the other hand, which makes us not hopeful, is that if you want to obey the structure of the hierarchy in the sense that the graph induced by your tree on any one part should be connected, sort of like similar to here, then there's like no hope for trees that are supposed to be spanning trees. In particular, there's this previous result, not stated in this language, but you can reinterpret in this language that shows that there are some graphs and hierarchies such that any spanning tree, importantly, which obeys the hierarchy in the sense that on each part it induces a connected graph, cannot achieve polylogarithmic distortion. Okay, so in particular, this is saying that you have no hope of constructing a tree embedding of this hierarchy that looks like the following on the green stuff, then connected on the red stuff, and connected on the purple stuff. So again, notice that like here this tree obeys the hierarchy in the sense that if you look at, say, this red part, the tree induces a connected graph on the red part. Okay, so that looks scary. Like it's trivial in the non-spanning tree case, but in some sense we know it's not possible in the spanning tree case. Okay, pause. Questions, thoughts, comments, boos, jeers. Okay, so all this is to say, our goal is to embed arbitrary hierarchies into trees. Trivial to do it if we don't want a spanning tree. Looks perhaps impossible if we want a spanning tree. Okay, so what did we show? Well, we showed that actually, you give me any gamma growing hierarchy, as long as gamma is at least log n, then you can embed its distances into a spanning tree in polynomial time, polytime computable, with only constant distortion. Okay, so give me any hierarchy that you want. I will take that hierarchy and I will generate for you a spanning tree, and that spanning tree up to constants is a good approximation for the distances in the hierarchy. And in particular, importantly, this spanning tree cannot obey the structure of that hierarchy. So it'll look something like this. So notice that if you look at the spanning tree on, say, this green part, it does not induce a connected graph, because like this thing is not connected to that, it's not connected to that. Questions. This is like the second and final major theorem I'm going to state today. Yeah.
Maybe I'm missing the definition. So when I look at the edge that cross the some high level components in the structure, that edge is supposed to have high weight.
No, so actually the weights of the edges in this tree will be the same as the weights of the edges in the original graph. So it's only the non-spanning tree case where we're going to modify the weights of the edges. But here I'm literally just taking a subgraph of the original graph where I inherit the weights from the original graph. Or you're asking, is it necessarily the case?
Yeah, it is necessary. Because it is, so the distortion means that pairwise just
Yeah. Yes. Yeah.
But then like within two versus, let's say, in the same green part,
Yeah.
That is not connected within the same green part. So it uses edges going out of it.
Yes.
The distance is more than gamma.
Yeah, so for instance, like the distance between this vertex and this vertex, according to the tree, will be whatever the one with this path is.
So why is this all one? Because the tree distance is like how much the screen size. Sorry, the
hierarchy distance
is how much the green size. The distance is.
Oh, like for this, like in this, I mean, this is, I guess, like an abstract representation of what's supposed to be going on. You mean like for this particular tree?
Yeah, let's say any tree that, let's say we focus on green part, there's not
Yes.
Then finding two vertices inside, the distance in the tree is supposed to be more than gamma to the I plus one. Let's say the green
Yes,
one.
for sure. Yes.
But why is that O one? Just this.
Well, so the like you need to guarantee two things. One is that the distances in the tree should only be larger than the distances in the hierarchy, and one is that uh, what you're saying, that like they should not be much larger. And so like if you have two things here which are not connected, say in the tree, then it better be the case that whatever the path is that connects them in the tree has length at most the diameter of the green partition. And what this is saying is that it will have the length of that path will be at most a constant times the diameter of the green partition. But like I haven't said that the length of that path is at least gamma to the I plus one. Like nothing about the definition should require that. Yeah. Yeah. I mean, you can imagine this path sort of like just jumps up for a second or something. Does not actually pick up a gamma factor. Okay, any other questions? Okay, so what's great about this theorem? I mean, it tells you that if you give me any hierarchy, I can give you back a tree where that tree is basically a spanning tree, where that spanning tree is basically a good approximation to the hierarchy distances. So jumping back to this picture, right, where we know that if you could come up with good embeddings for any of these hierarchies, you'd come up with all these senses of tree embeddings. It gives us like one tool that we can just hit like all of these things at once, right? Like we can take our embedding of arbitrary hierarchies into trees and take all of these existing constructions of hierarchies and end up with the kind of tree embeddings that we want. We don't have to do like one tree embedding per kind of hierarchy now. Okay, so what's the upshot of this? Well, for some of these things, of course, we know basically optimal tree embeddings already. But qualitatively, like the kinds of embeddings into spanning trees that you get, say, by embedding these LDD hierarchies, I think are much simpler than what we already know. Ditto for the Ramsey embeddings, and we actually achieve quantitatively better bounds for tree covers in universal Steiner trees using these new embeddings. So just because I've been focusing on universal Steiner trees, let me tell you all what you get out of this. So again, jumping back to this connection between universal Steiner trees and these sparse partition hierarchies, where we saw that embedding of sparse partition hierarchies was sufficient and that they exist. All we have to do is swap out the existing embeddings of sparse partition hierarchies with our new embedding of arbitrary hierarchies. And we'll change what was an alpha times tau into a constant distortion. Okay, and so then this gives you back a little implication, namely, if you give me alpha tau sparse gamma growing hierarchies, then I can give you back a universal Steiner tree that's not alpha squared times tau squared, but just alpha times tau times gamma times log a. Okay, and so coming back to our picture about what's known about universal Steiner trees, this gives you like a marginal. Using our existing hierarchies, this gives you a marginal improvement in the quality of universal Steiner trees by a couple of blocks. Okay. And in some sense, this is like minimal, right? This is like each parameter appears once and we pick up a log n. Maybe we don't need that log n, probably we need the other parameters. Okay. Questions about that? So again, the point is just like we embedded arbitrary hierarchies, whereas previously we only knew to embed sparse hierarchies. In fact, our embedding of arbitrary hierarchies is better than what we knew for sparse hierarchies. So that improves the quality of universal Steiner trees. Okay. So that's a hierarchy's perspective on tree embeddings. How much time do I have?
Less than 5 minutes.
5 minutes. 5 minutes or 5 hours?
If you stay one more day.
Yeah, so let me try and just tell you all a little bit about the proof sketches in my remaining 5 minutes. So again, the goal is we want to take an arbitrary hierarchy. It has some notion of distance. We want to come up with one spanning tree that is a good approximation for the distances in this hierarchy. Okay. So the basic idea is like some sort of top-down approach where we like start at the top level of the hierarchy. Maybe there's not that much for us to do there. Maybe we'll just like fix like one group at the top, something like that. Then we go down to like we go one level down. We like sprinkle in some edges based off of this level. Then we go one level down. We sprinkle in some more edges based off of this level. We keep doing this until we get to the bottom, where after we sprinkled in all of our edges, we end up with a tree. Very basic idea. A little bit more precisely, I mean, this is going to be a recursive algorithm. So let me tell you what it does for basically the ith level. So imagine that I'm thinking about some cluster at the ith level, and in particular, that cluster breaks down into a bunch of clusters one level down. Okay, so there's sort of like one implicit cluster lying around all this, and this is what would happen if we were to go one level further. We break it up to these green clusters. Okay, and now what I'm going to do is I'm just going to look at all of the parts that are incident to trees. Two edges that I've already added to my tree T. Okay, so maybe I'll mark this, and this, because these are incident to it, and maybe they're incident only at the last vertex of a path that I've added so far. I don't mark it. Okay, so it'll be like the solid edges and stuff. And then all I'm going to do is I'm just going to go to each of my existing parts. I'm going to look at the induced metric in this cluster, and I'm just going to like add a shortest path for each part to get to one of my marked parts. Okay, so for each part, this one, that one, so on. I'm just going to like add some path to get to a marked part. Got a lot of paths to add. Okay. Now, all I'm going to do is I'm going to do some kind of like conflict resolution. In particular, I'm going to take each of these shortest paths and I'll prefix them so that after taking the prefixes, any one part has at most one path non-trivially intersecting it. So that prefixing will guarantee that there's a sort of one path per part, other than sort of like the last vertex that it has, and at most O log n jumps to get to a marked part. Oh, I got to describe this. Okay, so the prefixing looks something like this. So you can see, like, I don't know, this long path gets shortened to just that. Up there, you can see like that long path gets shortened to just that. Okay. Okay, so you take these prefixes, and notice that like a single path can be non-trivially incident to a part, but it can like come and go as it wants. Okay, and I'll guarantee that there's like at most O log n jumps, which is to say that if you're this vertex up here and you wanted to get to a marked part, you can follow this path, but then you get stuck because you sort of like prefixed your path and now you know where to go. So you have to like take this jump here, then you can follow this, and then you have to take another jump, follow this, you have to take another jump, and I'll somehow take prefixes of these paths so you don't have to perform that many jumps. So the basic idea of the algorithm is some kind of cute, like, random permutation of the paths thing that's similar to Luby's algorithm, if you know what that is, parallel algorithms, or parallel maximal independent set. It's a very old result from parallel algorithms. And then what I'll do is I'll just recurse on each part. So I won't say too much about this, I guess, in this amount of time. But like the basic idea here is that like you have to perform these log n jumps. Since you recurse on each part, you have to pay sort of one recursive call for each of these jumps. But we know that gamma is at least log n, and so each of the recursive things that you're recursing on is like log n smaller, and these two log n's kind of cancel each other. Like the diameter of this green stuff must go down by a log n factor as compared to what you're currently looking at, and that somehow can be used to pay for the log n jumps. In particular, each of these jumps you're going to have to solve with like a recursive call. So you only have to pay log n recursive calls, but each of them is the log n smaller than what you're currently looking at. It's the rough equation. Okay, so then you like recurse on each of these things. You'll like look at the partition one level down. If you keep running this algorithm, you'll find that what you are computing is in a tree, but it's a tree that isn't rooted at one vertex. It's sort of rooted at the paths that you inherited from before, and in particular, it does not obey the structure of the hierarchy. So here, like this tree does not induce a connected component on this green set. That might look bad because, like, you know, if you want to get from here to there, say here to there in the green set, it's not clear how to do that because like you're not even inducing a connected graph, your tree. Like this thing can get to this marked part, this thing can get to that marked part, but they can't clearly get to each other. The second intuition I want to give you all is like, well, they can both get to this one path, and if you would pop one level up in your recursion, you'll remember that that one path is all part of a shortest path. So this is sort of like a super highway that allows the nodes to get to one another very quickly. So it's sort of like enough to get to that path, even though you're not connected internally in that part. Okay, that's my talk. Let me like quickly summarize. So basically, I introduced you all to this idea of universal Steiner trees. Previously, we knew Mary Poppins bounds. We improved those to polylogarithmic-quality. The way that we did that is we showed that if you can prove quality of, like if you can prove that there exist sparse partition hierarchies of some quality, then you can also get universal Steiner trees of that same quality. In particular, we just improved the quality of those hierarchies. We took a step back to tree embeddings more generally, and I told you all a little bit about how like, if you ever have any kind of vertex hierarchy, you can always take its notion of distance and embed it into a single spanning tree. This is nice because it sort of reduces the problem of representing distances in a graph to representing distances in a hierarchy, which is typically much easier. Like we know how to construct these hierarchies quite easily, but going straight for the tree embeddings is usually very hard. Okay. And yeah, I'll stop there for questions.
Can you say what's the improvement on tree coverage? You say you improve some coverage.
Yeah, it's not published yet.
Oh,
I probably, yeah, I shouldn't say too much. Yeah, but some results, yeah. There's other results in the paper, I mean, that are published about, say, like embedding hot constrained distances, which I didn't talk about. So you can get other stuff that I didn't talk about.
There are other structures on which algorithms are easy, but
Yeah, so one
intermediate structure.
Yeah, good. Well, I mean, one related, but well-studied, related but different, but well-studied sort of version of this is like rather than trying to embed distances into, say, a tree, suppose I want to embed distances into like a low tree width graph. So on arbitrary graphs, that's hopeless, but there's been a lot of work on like planar and minor free graphs that shows that you can achieve very good embeddings into low tree width graphs. And then low tree width graphs, oftentimes in the same way that trees admit good algorithms, also admit good or like much similar algorithms. So this led to the first F passes for a bunch of problems on planar graphs in the last 4 or 5 years.
Use this take width every time you pop.
Sorry,
Every
sorry.
time you recurse, can you increase tree width instead of try to be clever?
Every time you recurse, can you increase tree width?
Basically, okay, now it's not going to be a tree anymore, but kind of.
Yeah, I don't know. The techniques there are very different. I mean, because those techniques are very much using the structure of, say, a planar graph. They use these like shortcut partition things that like there's no hope on arbitrary graphs. So you somehow, I mean, if you want to do something like that, you have to use like planarity or minor frequencies. That.